Our title is graph-based knowledge distillation for unsupervised discourse fever detection. The name we chose is the TickNet AI for our model. These are the keywords. We are going to start with the problem statement that the cattle farmers in Uganda face the challenge of identifying potential outbreaks of discourse fever for early detection, as it is very essential in its control and management. So the proposed solution that we are designing a machine learning model for early detection of discourse fever by providing the real-time prediction and actionable recommendations to farmers to reduce the associated risks, such as the high mortality rate as the disease becomes severe or worsens within the cattle. The project's objectives is that one of them is to develop the model for early discourse fever detection. Another one is for providing or developing a cost-effective model that reduces reliance on expensive laboratory tests. Another one is enhanced rapid diagnosis, which provides results in minutes instead of the days, as the laboratory tests may not be instantly provided or the results are not instant. Another one is provide a scalable model that can be deployed in rural and remote areas via mobile applications. Since we have the APIs, these APIs can be deployed mobile applications for remote use. Another one is enhanced disease tracking through monitoring and mapping disease spread. Since our datasets contains the routines and latitudes, they provide the location, local data spread of the disease. And then the session overview about our AI machine learning model pipeline. The first step is that we are providing the data preprocessing and feature engineering, whereby we handle the missing values. These ones were handled by removing the rows that had the missing values, and then the graph-based presentation, we normalized it, make sure it is balanced, and then the dimensionality reduction to make it light for easy loading. Then we move on to the graph construction. Okay, nearest neighbors. This one is for graph attention mechanisms. We also have the graph constructive learning. They're all under graph construction. And then we do model optimization with knowledge distillation, where we come up with a student model, which is lightweight. And then finally, we have to do deployment and MLOps, a pipeline where we use Blender and simulate previously. The dataset used was a public dataset from Dryad Open Data Publishing Platform. This dataset had some missing values and then alphabetical values. It was also unbalanced ECF class. It was biased. The rows with missing values were discarded. And then the columns with alphabetical values were encoded, where it was the genotype, we made it 1 and 2. We made it 1 and 0. And then the excess rows, which made the dataset unbalanced, were also discarded to ensure there is no bias during the prediction. This is how it came out. You can see it was balanced for the 0 and 1. 0 represents the positive ESF, and then 0 represents the negative ESF. This is the heat map. The red parts indicate the high correlation for negative, and then the dark blue represents the high correlation for positive between the features. And then we move on to the models and techniques. The models used were graph attention mechanisms, graph neural networks, and knowledge distillation, plus unsupervised discourse, plus unsupervised learning. These models capture spatial dependencies in case of GCN. They also make the model lightweight in case you're using knowledge distillation. They also identify the high risk of characters in case of the supervised learning. And then the GAT captures the disease spread better than the GCN by dynamically weighing these neighbors. So these are some of the reasons that's why we chose to use these models. As you can see, these are the evaluation metrics of accuracy, precision, and different scores. We can see that this graph attention mechanism has the highest accuracy compared to the rest of the models. The system architecture, as I earlier said, we have the features in our dataset. We have the genotype and the cattle. We have the geographical data, we have the longitude and latitudes, and then the farm, we have the cattle density, and then also have the environmental data, which is temperature ticks and October values. Then we do data processing, which involves the cleaning, normalization, and engineering, plus graph construction. And then we move on to the model training and learning, which includes graph neural networks and supervised learning for clustering, as I said, and then traditional machine learning. Also have knowledge distillation to make light models, where we come up with the student models, and then we do prediction and deployment. And then this can be utilized by farmers, veterinarians, the genetists, or the policymakers. And then we have the implementation details. The language used during the implementation of the models is Python, while a number of libraries is using the Torch, the NumPy for handling the calculations, and then the Pandas for loading the dataset, and then the Matlib for constructing the visualizations, and then the scale mentioned by the few. Then the platform used is the Google Colab, which provides the CPU and then RAM, which makes it easier for computing resources. And then some of the results of the evaluation have the confusion matrix for the class, and the student models have the learning rates for the teacher and learning for the teacher model, and then the student model also have the accuracy matrix for precision F1 scores. That's the teacher model, and the student model uses the accuracy slightly a bit. Yeah. Let me invite my colleague.
Good evening, everyone. My name is Benham Shadrik, and I'll be continuing from where my colleague has stopped. And so I'll be talking about first the impact and relevance, where our solution will be aligned with the UN SDGs, where we have zero hunger, where we are saving cattle, and that we are saving food. We are also promoting food security. And then the third one is good health and well-being, whereby promoting animal health, in return it promotes human health. Then the ninth one, which is industry and innovation and infrastructure, It promotes AI for agriculture, which we are basing on to create our machine learning model. And our target users and beneficiaries include the veterinary clinics, livestock farmers, animal health workers, agricultural researchers, and government disease control agencies, where the Ministry of Agriculture may also lie. So if I talk about the intellectual property and innovation, the potential intellectual assets that are in our innovation, they include the graph-based decision algorithm, the data processing framework, and the diagnostic decision system, which are using to make the decisions for whether there is viscous fever at a particular farm or it's not there. Our idea is cooperatable in that the software implementation, including the code's data handling techniques, are cooperated to prevent unauthorized replication from unauthorized users. And the trade secrets, we also implement trade secrets in that our unique AI model, the unique AI model training techniques are protected as trade secrets instead of using patents for better competitive advantage. And the uniqueness or the novelty of our innovation is demonstrated in the following ways, where we have unsupervised learning for viscous fever detection, where there's no need for use of live datasets, and a graph-based approach, where we don't use CNNs, and this method captures relational patterns in cattle and health data. So if I talk about the monetization and scaling, our solution, we plan to commercialize it in the following ways, where we have a subscription model where veterinary clinics and livestock farmers pay monthly or yearly fee. The NGOs, we license the AI model to the government or the NGOs, including FAO Uganda, or we can also commercialize it in pay-per-use API, where the research institutions and the diagnostic centers, they pay for the test per test conducted. And the potential market size, so Uganda alone has over 14 million cattle, and viscous fever is a major concern for small-scale farmers. So if we are to expand to the East African region, countries like Kenya, Tanzania, and Rwanda carry out cattle farming, and it's one of the major economic activities. So the estimated market size is then over $50 million in East Africa alone, considering disease prevention costs and AI adoption trends, which are happening right now. Enough so that we can reduce the losses incurred by farmers from the bad effects caused by viscous fever. So our interface, as you see, it is lightweight and easy to use by the farmer. And here there is a space for we have two options for upload CSV and for manual input. And we are going to explore the manual input where we are required to input the values for tick density, the cape, and if I to remind ourselves, the cape is they are the cape buffaloes which are the carriers of the ticks that spread viscous fever. Then this one is cattle density, and the by 5 is the temperature variable in simple terms. So here we already have pre-written values where we have the tick density, we have written 10, the cape we have written 1, because you may be in an area because remember these cape buffaloes are located in areas near game parks. So if you're in a place which is not anywhere near game parks, you can put 1 or something less than that. Then we can put cattle density, I put 60%, depending on how much cattle you have on your farm. Then the by 5, I put 37.00 degrees Celsius. And depending on what you want, you can either choose to use the teacher model, or you can either choose to use the student model. But right now, you're going to implement using the student model. And once we finish inputting that, we press on predict. But since we want to save time, so we have already gotten the results here, and it brings prediction successful. And once the prediction is not successful, it will still bring an error message and won't bring any results. So from the results you have input, we see that our prediction is 1, and from what we know, that 1 represents that there is a high risk of viscous fever, and the confidence level of the model is showing it's 100%, meaning that the model is highly confident that there is viscous fever on this kind of farm bearing such results, such initials which we have put in those in the features, the tick, cape, and cut and by 5. And the class probabilities, these ones are confirmatory results to show us, to confirm this prediction. Now the class 0, it shows that there is no risk of viscous fever, so it's telling us that it is 0, 0, 0, 0. That means it is completely sure that there is no low risk of viscous fever. And for class 1, it's showing that it's 1, so which is 100%. So it's 100% sure. It's 100% 1. So it's 100% sure that there is viscous fever at such and such a farm. So that's our system implementation. Thank you. So these are the team contributions. These are team contributions per member. Well, in this group we are 2 people. Yeah. And the lessons and the challenges, the lessons learned and the challenges. First, we had teamwork challenges where we had workload balancing, handling both technical and business research, and then time management and deadlines, where we had the challenge of juggling the AI development, research, report writing, and presentations while managing other academic commitments, which was very stressful. And the technical challenges, we had unsupervised learning complexity, where the training the hybrid model with knowledge distillation was difficult, and the feature extraction complexity, where identifying most relevant features for disease detection was also difficult, and integration with the cloud, where deploying the model efficiently on cloud platform, it posed very significant challenges. And the lessons learned from this, we have model optimization, which is key, and collaboration, which is very critical, and data preprocessing, which is very important. And our future work, we propose to improve and add to our innovation by expanding on data sources, where we can have another data set to help our model learn better, and also apply AI deployment, where we deploy our AI model on power IoT devices that farmers can use them on their farms. And then we also plan to scale and extend our work to regional and global expansion, where we plan to scale beyond East Africa and West Africa, South Africa, where we know that they also carry out livestock farming, and also integration with veterinary systems, where we plan to collaborate with the Ministry of Agriculture and veterinary clinics to integrate the system into existing livestock health programs. And in conclusion, the key achievements that we developed a hybrid machine learning model. We integrated graph neural networks and supervised learning and legislation. We address challenges of imperfect data and imbalanced classes through data processing and data processing and data cleaning, and we created a lightweight model using distillation for mobile deployment. And the value of our solution is that it provides a timely and actionable information for farmers for early detection of viscous fever. And the impact of our solution is that it will help farmers to detect viscous fever as early enough in order to reduce the number of losses on the number of cows that die, which reduces the mortality rate of the cattle, increases the mortality rate of cattle. And in conclusion, the machine learning models, especially unsupervised and hybrid approaches, they significantly improve viscous fever detection. And applying advanced machine learning technology, it plays a very vital role in improving livestock and health and economic benefits. So that's it from me. If you have any questions, you can consult us on